In the talk, I want to share with you some of my thoughts regarding the possibility of testing causal dynamical triangulations, CDT for short. I'm sure that most of you already know basics of CDT. Therefore, I will be very short in introducing CDT. I mean, four-dimensional CDT. So CDT is a very conservative approach to quantum gravity based on path integral approach to quantum mechanics, with action being just a sum of the Hilbert-Einstein action and the action for cosmological constant. And then Euclidization of the theory is performed, and then in order to put everything on computer, you have to discretize the theory, and then you have the partition function that you can simulate, and then you have a many-body system actually that you simulate on the computer using Monte Carlo computations, which are mostly done in Cracow at supercomputers. So what the results are. Here I want to focus on the two aspects, two characteristics, features of CDT. The first one is non-trivial phase structure CDT. At the moment we know that there are, previous results have shown that there are three phases C, which is, let's say, the classical one at the large scales, the four-dimensional, and the Sitter space is recovered. At the short scales we have some quantum behavior. We have some non-geometric phases, in particular the phase B, which is so-called crumpled phase. And we have a phase A, which is, let's say, sort of dispersed state. And recently a new phase has been discovered, which is kind of sub-phase of phase C, which you can see by investigating more sophisticated order parameters. And there are phase transitions, in particular the second order phase transition and the first order phase transition. And I will be talking later about more details of that. Another feature, you can characterize those phases by different quantities and by different characteristics, and one of them is scaling, which is related with the in particular different dimensions which characterize the different phases. And especially I want to focus on one particular observable which has been studied since quite a long time, which is spectral dimension characterizing the phases. So because I will base quite heavily on the concept of spectral dimension, just let me, sorry? Yeah, the kappa 0 and delta parameter are Baire parameter in our action. Okay, so roughly kappa 0 is related to the inverse of the Newton's constant, and the delta parameter is kind of parameter, effective dimensionless parameter, which characterize relation between a spatial and temporal links in the discretization. Okay, so it's related with the speed of light actually. And yeah, so in order to define a spectral dimension, let me start with the heat kernel equation, which is just the diffusion equation with the initial condition being a Dirac delta function. And then we have the Laplace operator, elliptic operator here, for which you can study the eigenvalue problem, and using the eigenvalues and eigenfunctions you can write a solution to this equation in this particular form, which will be useful later. And then you can study an average return probability, which is just a trace of the heat kernel, which gives you the density probability of giving back to the initial point in your random walk process. So dependence is such that you can defining such quantity for Euclidean geometries. For the Laplace operator defined on Euclidean geometries, your spectral dimension just gives you the topological dimension. But in other cases, when you have your Laplace operator defined on some quantum spaces, you will have a different results in general. So in CDT, It's already a 10 years old result, that in one particular point of the phase C, we observe running of the spectral dimension such that at the large scales you have 4 dimensions, you recover 4-dimensional space-time. But if you probe your space-time at the short scales, your dimensionality falls to 2. It was done, I mean, these results were done at one particular point in the phase space, but recently more studies have been done in the phase C, especially when you go towards the transition, second-order transition line with the phase B. As you know, around the transition, second-order transition, the fluctuations are high. I mean, it takes a lot time to thermalize for your system. Therefore, previously it was difficult to perform the simulations there. And recently, due to the improvements at the level of the computations, it was possible to prove to show that this dimensional reduction in the different parts of the phase C might be different than the 2 value. So right now I want to make use of that. I want to make use of this particular running of the spectral dimension. And so what I want to do with this. So let me go back to this definition, to this solution to the Hitchcock equation I wrote before, and taking the trace, I introduced the average return probability, which is, as we know, a function of the eigenvalues of the Laplace operator. And the eigenvalues of the Laplace operator, just in 4-dimensional Euclidean space, are just it's just a Lorentz is just a Laplace operator in the Fourier space. Okay. So you see that there is a relation between both. I mean, between the spectral dimension and momentum space representation of the Laplace operator, and we know that from the momentum space representation of the Laplace operator, after performing the weak rotation to the Lorentzian space time, of course, which is possible for the holomorphic functions, we can get dispersion relation. This is the classical case. In general, for the different different possible Laplace operators, which are defined not on the Euclidean spaces, we expect that the diffusion time dependence of the spectral dimension will be different than the classical one. So what I want to do as a first step here now is to try to recover the form of the momentum space representation of the Laplace operator for a given parametrization of the spectral dimension dependence on the diffusion time derived from CDT. So you can explicitly do that, but only because you know you want to recover a function from another function, but in general your momentum space representation of the Laplace operator is a multi-variable function. So then it's impossible to recover the shape of this function knowing a single variable function by some transform. Therefore, we have to parameterize somehow our Laplace operator, and here I choose this one particular form of the parameterization of our momentum space Laplace operator, such that then if we recover dispersion relation, it will have this form, such that omega function, which we want to find, will classically, in a classical limit, will be just equal pi. Then one more thing, just for simplicity here, I fixed that at large scales, for large diffusion times, I precisely get 4, okay? And here in the UV limit, my dimensionality will be 2 plus some little deviation, but we can generalize this result to any DUV, and I did it, and I will comment later what are the results in all the possible cases. But let me right now focus on this particular situation just to be more concrete. And then, I mean, you can find the relation between our omega function and our return probability function. Then you can invert it by virtue of the inverse Laplace transform. And then, on the other hand, knowing the result, the parameterization from CDT, you can recover from definition the form of the return probability for the CDT parameterization, and then combining both, you can find the dispersion relation. I mean, relation expression for omega in such non-explicit form given by confluent hypergeometric function. So in order to see what it really gives us, let me plot the function omega versus momenta. So we see that at low energies, okay, when your energy scale is smaller than energy scale of the dimensional reduction, you recover the classical theory. But then if you go to the quantum domain, you get deviation, deflection from the classical dependence, and these are two asymptotic behaviors. Okay, so in the infinite limit, which is here, you have the linear dependence as in agreement with the classical theory, and then you have a cubic deformation here in the first to the leading order. And then in UV, you have this power law dependence, which I will investigate later. So what we can do with that, we can apply the deformation, the dispersion relations in particular, I mean, to the different fields for which we have in equations of motions Laplace operator. So in particular, we can apply it to photons, we can apply it later to cosmological perturbations and do phenomenology based on that. So the first thing is something what we very well know since late 90s by seminal works by Amelino Camellia. So we know that we can actually try to constrain those kind of effects using astrophysical photons originating from astrophysical sources as gamma ray bursts. We can study the group velocity and see how propagation of the high energy particles is affected by this effect. You can study this, but here, because of the effect is predicted to be the quadratic one, the energy dependence is quite weak, and therefore the constraints on the energy scales of the dimensional reductions is not very strong. Anyway, using astronomical observations, you can put a lower constraint on the value of the E star, which is anyway much stronger than any constraint you can imagine based on Earth-based experiments. Okay, so you can, with this constraint, you can exclude some low energy dimensional reductions. Okay, but okay, you can do much more regarding using the astrophysical constraint, but basically you would not expect much with that. Another possibility to relate these effects with some observations is in cosmology, especially in the cosmology of the very early universe, and especially in the process of formation of the primordial perturbations. And then there was very interesting observation made in 2013 by Amelino Camellia, Arezano, Gubitosi, and Magheggio, which observed that if you have dimensional reduction to 2, so something as you can get in some points in the CDT phase diagram, your vacuum normalized power spectra in the UV limit will be scale invariant. So that's quite a nice observation, because you may expect that maybe you can somehow relate it with the cosmological observations, which indicate that we observe nearly scale invariance power spectra of the scalar perturbations. And even more, it may give an alternative to the theory of inflation. We know from the talk by Aurélien that in fact inflation doesn't help us to study quantum gravity effects in the early universe, so it would be better to just study them directly, and that would be possibility. Unfortunately, as I will show you, I mean, those predictions are that we actually get here after combining the scale invariant spectrum in the UV limit with large scale spectrum gives a result which is in contradiction with observations. I mean, in this scenario, okay, I will talk about other scenarios as well later, okay, if time will permit. But within this scenario, everything, other problems are solved in precisely the same way as it's done in inflationary paradigm. So just a very short reminder regarding the theory of perturbations, formation of the perturbations. We decompose any field, scalar perturbation, tensor perturbations, for the Fourier modes, and the Fourier modes then are quantized. We are working in the Heisenberg picture, so the operators are evolving. And then for the Gaussian fields, on which I will focus here, all the evolution can be contained in the so-called mode functions, which multiply annihilation creation operators. And then, because of the classic canonical commutation relations, we have the Wronskian condition, which gives us another condition on the form of the F functions. And then for Gaussian perturbations, all the statistical information about the perturbations is contained in two-point correlation function. So this is all what we need to know about the random field that we study. And instead of two-point correlation function, the vacuum expectational value of this product in the vacuum state, we can study the power spectra. And yeah, we have the mode function there. Z depends on the form of the perturbations that we consider. And then we have equation of motion for F, where there is k square here, which comes from the Laplace operator. So this is classical expression. Because in CDT, okay, we have this dimensional reduction. The Laplace operator, the spectrum of the Laplace operator is different, so we can take into account replacing the k square by the omega, and we take into account here the fact that the k is a co-moving non-physical momenta, so we have to take into account by introducing the scale factor, and then this is our equation. So depending on Z, we either have tensor or scalar perturbations. So we can choose the ordinary vacuum normalization for the modes, and then we can study what the spectrum is. So in the very deep quantum regime, when the omega has this form of p to the power of 3 plus the correction, we indeed have power spectrum which is nearly scalar invariant. There is epsilon deviation here only, so for dimensional reduction to 2, epsilon is equal to 0, so we have a perfectly scalar invariant spectrum. Here I wrote a spectrum, for example, of the barotropic matter, but you can study other types of matter. In particular, you can study slow roll inflation, but the results will be similar. I did it, but I don't show it here for simplicity of the presentation. But then you have to consider a freeze out of those modes. Okay, so you have your modes in the UV limit, but then you want to see what will happen with those modes when they will be redshifted and they will cross the horizon at some point. So if you would like to have your spectrum to really be produced in the deep quantum regime, then your scale of your, inverse of the energy scale of the dimensional reduction has to be greater than the Hubble horizon scale. And then you have a freeze-out taking place already in the deep UV region, okay? Otherwise, if you interchange those two lines, you will have production of your perturbations already in the classical domain, so you expect the classical result there. You can consider something in the middle, but results will be very similar. So then the condition of the horizon crossing at which the evolution of perturbations changes qualitatively is given by this one, by this equality of these two contributions to the equation for modes. And then what you will find, firstly, you can study what is the tensor to scalar ratio, good. And you will see that this is this quantity. So from the observations, this is classical result. This works for all possible vacuum normalized perturbations independently on what is the form of your dispersion relation. So it gives you a very important constraint that your W has to be very close to -1. So anyway, you still need to have inflation there, okay? Your omega has to be in the barotropic equation of state has to be very close to -1. So anyway, you will not, with this process, you cannot replace inflation. It must be there if you want to fulfill requirements of the constraint from the CMB observations. Another thing, then you can study what is the scalar index of your spectral index of your scalar perturbations, and then you will find this expression, and this expression taking the value from the scalar perturbations from the measurements by Planck and Bicep, you just apply this equation to this formula and then use the constraint on R. It gives you that epsilon has to be much greater than 0. So, and this is in contradiction with the initial assumption that epsilon has to be small. This formula works for small epsilon, but you can generalize it. I did it for general DUV, and it never works. Okay, it never works. There's one possibility to get agreement with observation at the level of scalar spectral index. Such that you don't have the dimensional reduction, but your dimensionality is growing. Okay, which you might observe in some situations, but even there's another problem, which is at the level of the amplitude of perturbations. If your amplitude of perturbations is formed in the UV limit, then coming back to this expression, you will see that this has to be very close to 0, so this is big number. Then E star versus E Planck is of the order unity, and then you will have some contribution which is much greater than unity there. So the amplitude will be in that case greater than unity, but from observation we know that it's 10 to the -9. Okay, so you have something which is completely in disagreement with observations. So that's a bit pessimistic, but okay, we show that the model is indeed in it doesn't agree with observation. That's nice from the other side, because we learn something. We know that something doesn't work in reality. Okay, so the cosmological observations are already such restrictive that we can exclude something. Okay, so that's good. Another possibilities. Okay, let's go back to the 5 minutes. No, I'm finishing 4:15. Okay, good. So my initial expectation was that, okay, we live somewhere here at the phase diagram, and then we observe the perturbations which were formed somewhere else in the early universe, and from the point of view of the renormalization group flow, we have some particular path which is chosen by nature. We are here, and we observe primordial perturbations which were formed somewhere at the larger energy scales, at larger temperatures. So maybe by using observations, we can point out where at the phase diagram in the early universe the perturbations were formed. And it would give us, because at different points we have a different DUV, different dimensional reductions. So my initial expectation was that maybe using these observations we can point out where in fact those perturbations were formed in this phase diagram. Unfortunately, I mean, due to this, what I already told you about, and I investigated this issue quite extensively for the different models, it never works. Okay, so it doesn't work. But there are some other possibilities still. You may go further back to the transition line with the phase B. So the transition line between the C phase and the B phase it has been measured that it's of the second order. So we have critical behavior here, and you may expect, okay, such you may think about the possibility that primordial perturbations maybe can be formed here, and there might be a mechanism to generate nearly scalar invariant perturbations here. Actually, this transition between the B and C phase is something what was actually discussed this morning by Daniele. Okay, so this is actually an example of Geo Metro Genesis. Okay, the B phase is non-geometric phase, is a phase which can be described by highly connected graph. Okay, so you have no notion of locality. You cannot introduce any coordinate system there. There's nothing like there exists, and it has been measured, is reflected by dimensional, by Hausdorff dimension going to infinity, because you can go from one point to another just in few steps, okay? And then if you go to the lower energy, if you let's say decrease your temperature, at some point the second order transition takes place, and you may pass to the geometric phase where the notions of like coordinate system and metric has a sense. So that's a possibility, and the question is whether really we can extract something from that. We know that at a critical point the correlation length goes to infinity, so that's nice because we have a scale-free dependence on the level of the correlation function of our order parameter, but we don't have a scale freedom. Scale invariance, we have scale freedom, but there are some scaling parameters still depending on the dimensionality. So the scale freedom could be recovered only if at the second order transition line the dimensionality, topological dimensionality, would go to 2, plus some deviation, which is of the quantum origin. There has been some approaches where people try to extract something cosmological from here, but you have to judge by yourself those approaches by yourself. There is another possibility here. Okay, I don't know whether we can generate scale invariant power spectrum from a second order phase transition or not, but we can do something different. We can already check whether we can disprove it. Okay, and this is related to the generation of topological defects. And I mean, usually, I mean, when we study thermodynamics, we consider equilibrium systems, okay? But in reality, passing through the transition point always takes some time. And if we introduce time to the game, we enter the field of non-equilibrium processes, and the formation of topological defects associated with the second order, in particular second order transition, is explicitly a non-equilibrium process, which is because, okay, you have your high energy phase, and then you pass to the low energy phase, and then you know that the correlation length goes to infinity, at the transition point, and then your relaxation time goes to infinity as well. It's because the fluctuations at the transition point. So it takes long time for the system to establish an equilibrium state because of that. And you can, and very interesting observation made by Jurek and Kibble already in the 70s and 80s is that you may gain information about these non-equilibrium processes using the observables that you know and the behaviors that you know from equilibrium phase transition physics. And this is, so let me introduce one quantity, which is just the relaxation corazon, okay? So let's say that you have 1 minute, okay? You pass from the high temperature state to low energy state, and then in different points of time your system relaxes to the new phases, and this information spread with some rate, and then on the other hand your correlation function is decreasing, and they meet at some point, and you have the freeze out, and you have the formation of the domains with the different vacua. So you can see that you have this size of your domain, and you can say that, okay, let's say that there was no inflation, and we had, let's say the universe was dominated by radiation after that, so you can see what, for the typical sizes of the domains just derived from this formula, what are the present sizes of those domains, gravitational domains. So you get 1 millimeter. So this is something what is explicitly in contradiction with observation. So you have to introduce inflation anyway here, just to dilute the density of the gravitational topological defects in the similar case as it was done originally in case of inflation with the grand unification scale defects. Okay, so it doesn't work again. Okay, so let me conclude. Phenomenology, yeah, so I've shown you an example that you can really build some phenomenology based on CDT, and you can really try to falsify the theory based on these predictions. You see that some models can be really excluded, and they are in disagreement with observations. Of course, to make those predictions more robust, you still have to study more different possibilities with a different UV, but this is what I already studied. And I didn't study different parameterization. This is something what can be done already as well. You can introduce curve momentum. So what I assumed here is that the momentum space is flat here, but we know that it may introduce some additional effects. But at the level of the studies already did with the different DUV and with different background dynamics, we see that the results are always in contradiction with observations. We have the phase transitions, which is kind of new possibility, but at the moment we don't see any direct mechanism to generate primordial scale invariant, nearly scale invariant spectrum of primordial perturbations here. You have this critical behavior, and you can study non-equilibrium transitions. This is very interesting in itself, but I mean you can make such a funny predictions regarding the concentration of domains, which explicitly might rule out some of the possibilities. Of course, still a lot of things remain here just to define what the defects are. You have to study the homotopy groups, for example, I mean to see the details of those defects. So at the end, just I wish you a lot of disproved quantum gravity models in your studies, because I mean this is the only way we can really learn something about the Planck scale, and I hope I just shown you one example of that. So we go ahead. Yeah, thank you.
So I'm pretty sure. I'm pretty sure the calculation is wrong.
Sorry?
I'm pretty sure your calculation is wrong, but I'm not sure exactly where. So the first thing is you cannot have an inflationary equation of state and do this calculation.
Sorry, I can hear you.
Your calculation is wrong.
Your one is wrong. You didn't.
No, wait. So I'm not sure exactly where the assumption is wrong, though. And the first thing is you cannot assume an inflationary equation of state.
I mean, what can I say that there are flaws in your paper, okay? I mean, you haven't studied things properly, okay? So, I mean, that's the honest truth.
No, let's go back. So if you could perhaps show the expression for R. Let's start with the expression for R.
Yeah.
Okay. So I'm not quite sure how you fix... Okay, that one. How did you fix the amplitudes?
Sorry?
How did you fix the amplitudes?
I mean, the amplitudes here are vacuum normalized, okay? So look, see, under the horizon, when this condition, I mean, when this guy is bigger than this one, okay? So if you go back to the equation for your mode functions, okay? The sub-Hubble domain, okay, regime is where this guy dominates over this one. Okay.
Yeah, sure. I know.
And
that.
you can apply. You can extend this. I know, but you want to see.
So the question is the following: there's one way to do this, which is simply the ratio of the Planck scale with the energy scale when you leave the horizon. This is true for inflation. It's true here as well. Okay.
Can hear you once again.
Okay, I repeat. There's one way of computing these, which is valid for inflation, valid here. Forget this formula, which is simply the scale of the the ratio of the Planck scale and the energy scale when you leave the horizon.
Sure.
You know this formula?
Yeah, sure.
So basically, this energy scale is a scale in which you cut off the equation, the dispersion relation. Yes or no?
I mean,
yes or no? No, forget that formula.
I'm not sure whether I understand you correctly. Therefore, I would prefer not to answer to confirmatively, okay, or affirmatively.
No, this is a simple calculation. This is a simple result in inflationary cosmology and any cosmology. Okay?
Yeah. But I don't understand what do we understand correctly.
No, is this true or not? I mean, if you understand this or do you not understand this, that is the question, right?
You can discuss it in private. So, any other question?
Was your question related to the amplitude of perturbation? How you fix it at the?
I think this is long, so you can probably discuss it over the coffee break. It's okay. This is going to go on for a while.
No, I don't want to lose it at this level. Okay, let's clear it up. Okay, let's clear it up because I'm pretty convinced that everything is here correct. You had. Because the way he answered, he asked the question was not much clearer to me. I mean.
All right. Why don't you discuss some coffee and then just give you a minute before we start the next lecture and you actually tell everybody what you agree and what you disagree on. All right?
Okay. Let's do it like that. That's fine. That's perfect for me.
Right. Yeah. A very quick question. You were drawing the RG flow in the CDT case in the phase diagram, and you were considering the region close to the phase transition to be the early phase of the universe, of course, in accordance to the Geo Metro Genesis idea.
That's a possibility.
Yeah.
That's a possibility.
But so I agree with what you said and what you have done, but I think it's very subtle in the sense that why would we associate the RG flow with the temporal flow towards the early universe or the other way around or in any other direction?
You may introduce some, let's say, energy scale which flows when you go. I mean, for example, energy density of the universe, which is kind of characteristic.
My question is, so I know the issue, so that's why I'm saying I was just pointing out that the association is not straightforward at all,
of course,
conceptually
sure.
and technically. So I was just wondering if at this stage you were just assuming it as a way to interpret what you see, or you had some special reason for arguing that is the right way of interpreting physically the flow.
No. I'm not saying that this is what is happening really, okay? There are some hints regarding the RG flows lines which are coming from this paper, okay? This is something very preliminary, which just give you a hint that the RG flow line may go in this direction, okay? How it's related with the evolution of the universe, this is another issue. One of the possibility is that you see that as you do it in statistical physics, you have your partition function, and all your coupling constants are multiplied by 1 over T, 1 over temperature, okay? And then on this plot, that would mean that the changing of temperature would correspond to the just one line on this plot. And if you have an environment in which your gravitational system lives, okay, then, for example, matter may play the role of your environment to your system, then you may introduce the heat bath, and you have a temperature, and you may control the phase transitions in your gravitational system. That's one possibility that I see, okay? You may reformulate your, I mean, it's a matter interpretation. You can take a look at the partition function that you study in the different ways. Either you may study that what you are considering is thermal field theory, and your field is gravitational field in this case, okay? So thermal field theory is one possible look at that. Another possibility is a field in zero temperature, okay? But on the other hand, you have running of your coupling constant because, yeah.
Okay, so let's thank Jakub again.